So please help me welcome Leo Fang. He's going to be talking to us today about CuPy and his journey towards GPU-accelerated computing in Python. Leo is a senior software engineer at NVIDIA and is currently leading the CuPy Python program. So please, let's welcome him, and then we hand it over to Leo.
Thank you, Nadi, for a kind introduction. And I also want to thank the SciPy organizing committee for having me here to give a presentation. It's a great honor and a pleasure to be here. So I'm Leo Fang. I'm currently a tech lead of a CUDA Python program at NVIDIA. But today, I want to share with you some of the personal stories I have and some of the projects I've been working on since a long time ago, way before I joined NVIDIA. And the project is called CuPy. So for those who don't know already, CuPy has been positioning itself as a drop-in replacement of NumPy on GPUs. So all the NumPy APIs would work on GPU if you switch import NumPy as NP by import CuPy as CP, and then use CP everywhere in your code base, right? So CuPy has been primarily developed by the company in Japan called Preferred Networks, PFN. It's because they want to use CuPy as a computational backend of their machine learning framework called Chandler. And Chandler back then was very popular, but then they cut it off and switched all the efforts to PyTorch. But CuPy stays and evolves into the fully open source projects that we see today. So my story today begins with this screenshot I take from the CuPy website. And I wanted to show you why, in addition to Preferred Networks and obviously NVIDIA, there's a third logo shown here, which is Brookhaven National Lab. So it's all started with my first ever HPC project called X-ray ptychography. Basically, it's a computational macroscopy method that X-ray beamline scientists use in synchrotron facilities routinely. So what they do is that they scan through the sample using X-ray and collect all the diffraction patterns from the detector, and then feed the diffraction patterns into various computational intensive numerical inverse methods to reconstruct the sample image based on the experimental data. Back then, we needed to accelerate the Python code developed by the scientists at Beamline because the Python code was way too slow. Constructing a typical experiment took several hours to do, whereas after all these efforts, we narrowed it down to only a few minutes. I would love to dive into the science part of this X-ray ptychography, but however, I don't think I have enough time for today. And also, there will be a talk given by Shihir Karakuzu from Brookhaven about the latest progress in X-ray ptychography there. So I would kindly point people to her talk also in this ballroom later today at 3:25 p.m. But it's suffice to say that for computational purposes, we just need to focus on a lot of FFT that we do in X-ray ptychography application, and there are also a lot of reduction operations and element-wise operations that we need to do. So it makes it a very ideal application for GPU acceleration. So after some evaluations, I started contributing CuPy, thinking that CuPy is the ideal fit back then and to help us accelerate our code. And typically, as I mentioned, CuPy is a drop-in replacement of NumPy. So this is a familiar NumPy code, except that the import is replaced by CuPy, and you use CP or CuPy everywhere. This looks familiar. This is kind of a typical step in ptychography. We need to sum over all the elements in the image. And it works for CuPy out of box since CuPy v6, which is a very long time ago. But we noticed that there are some performance improvements. Specifically, CuPy has this general purpose reduction kernel taking care of array input with different dimensions, different strides, different shape, and so on. But most of the time, when we do a reduction in ptychography, we just have a contiguous array. So you don't need to worry about strides. You just sum over them as quickly as you can. So we realized that NVIDIA has this CuP library that provides a lot of high-performance parallel algorithms, including reduction. So starting in CuPy v7, we allow CuPy users to build CuPy from source using CuP, and then after they turn on some flags, they can accelerate the same code by more than 1 order of magnitude. So after seeing some benefits in CuPy V8, we say, hey, that's great. Let's incorporate this change into the CuPy wheel so that users don't have to build from source anymore. You just guard it again, behind a flag, and users who want to use CuP acceleration can turn it on by exporting an environment variable, CuPy accelerators, equal to CuP. And the same code will work out of box without any change in the code, and it's accelerated. Finally, in CuPy version 11, we decided that, hey, CuP is good, very good, and there's no reason we don't use it as a default. So now we switch it to be a default. So another thing we noticed through the analyzing and profiling the performance of X-ray ptychography on GPU is that FFT plane management can have a non-negligible overhead. And for those who use FFTW on CPUs already, you know that in order to perform FFT performantly, you need to create a plan, and sometimes getting an optimized plan can take time. And the same story also happens with cuFFT. So this is an example using cuFFT under the hood to do a batched 2D FFT complex to complex transform. And it works out of box again already in CuPy early days, but we noticed that if you allow reusing the plan instead of recreating a plan every time you call FFT, actually you get at least 3x performance speed up. Right, and so in CuPy v7, we allow users to do this by explicitly managing their own FFT plan and then either pass it as a function argument or use it as a context manager. Either way will work, and you get a performance boost. So finally, in CuPy v8, we decided that, hey, instead of users having to worry about this, let us manage the plans behind the scenes for the users. So again, the same code would work as it was back in version 6, but now the code is accelerated because CuPy has a plan cache under the hood to catch all the common plans for users. And for advanced users who want to manage the plans themselves, we also open up the plan management API for users to control. Right. So using this application as a guidance, I went everywhere basically in the CuPy code base trying to improve the performance or add new functionalities and so on and so forth. And for example, complex numbers was not there yet, so I kind of added a lot of complex number support so that it's a truly general purpose numerical library instead of targeting originally like machine learning only. And one thing led to another, eventually kind of become a regular contributor contributing to CuPy. And after I was promoted to the assistant scientist, I got my own research grant from the lab, and also so that I can use it to support myself in part to do part-time development of CuPy. And this is why the Brookhaven logo was shown there. So I want to wrap up with my personal stories with kind of things I learned from interacting with open source for a long time. So the first thing is that it's not uncommon that we need to step out of our comfort zone and learn a new thing or to kind of advance our career. Right? I didn't know CUDA, so I had to learn CUDA, and I didn't know C++, so I had to learn C++, so on and so forth. And all these turning points make who I am now today. The second thing is that users, for better words, they really want to write simple code that just works. And a lot of times it's our job as a library developer to help them squeeze out every possible opportunity to accelerate and make their code faster. And so if you have awesome changes locally, consider kind of polishing it, and don't be shy from hiding it to the public. Look up the contributor guide, look up the developer guide, look up how other people submit PRs, and submit your PRs to the repo and upstream it so that all the users can enjoy your awesome changes and you can make an impact to the community. And the fourth thing is that, yes, while adding new features, adding new optimizations, it's exciting, it's rewarding, it makes it feel good. A lot of time we are really dealing with all this day-to-day maintenance works. For example, when a Python version is out, when a new NumPy version is out, new SciPy version is out, new CUDA version is out, new rough version is out, new Flag 8, and so on and so forth. How do we catch up? How do we suppress all these issues and evolve with the community? So really, we want to see more and more people try to help with the open source projects to evolve and keep it alive. And finally, you always want to treat people with respect, even if you might have disagreement with certain decisions that others make or certain viewpoints others have, because they, at some point, may become your colleagues, may become your manager, may become your customers, and so on. So keeping a healthy, long-term working relationship with everyone in the community is also important. All right, so let me wrap up with my personal story and switch gear to the latest progress in CuPy. Basically, this is the most single important slide. If you want to have a TLDR, you want to take a screenshot or take a picture, this is the slide you want to take. CuPy today has become way beyond something just for dropping replacement of NumPy. It's also covering up a significant portion of SciPy APIs as well as a Numba for NVIDIA GPUs. So again, CuPy is an open source project, it's non-focus affiliated, and you can pip install it or conda install it, and it comes with CUDA 11 and 12 support currently. And so the instructions shown on the screen can be easily changed if you want to CUDA 11 support. You just switch 12 by 11, it will just work. But the caveat is that we plan to deprecate and the CUDA 11 support very soon. And the CuPy namespace covers most of the NumPy API functionalities. And if you want something outside of NumPy, then you look for this CuPyX namespace. For example, CuPyX.SciPy covers SciPy APIs, and CuPyX.jit covers Numba APIs. So because a lot of math routines in NumPy and SciPy, they are kind of established for many years. We do know how to map this high-level Pythonic API to underlying math primitives. So when we add GPU support for these NumPy APIs, we can easily find vendor-provided, expert-tuned GPU-accelerated CUDA-X libraries. So for linear algebra, for the dense or sparse, FFT, random number generation, and so on, we always can find GPU-accelerated backends and try to use them as much as we can. However, even for integrating with these libraries, sometimes it's non-trivial. Sometimes the library API is not as simple as just call this API. Sometimes you have to pre-process your data to match what this API expects. And sometimes you also need to do post-process of the data after you call these APIs to match what NumPy expects, for example, because NumPy has certain expectation for what data, what arrays it should return. And we want to follow NumPy's footsteps. And in particular, array operations, this is a completely empty. As far as we know, there is no well-established libraries that provides array manipulations such as getters, setters, fancy indexing, and copies, and so on. So really, a lot of things we have to write from scratch with some custom kernels. So libraries are great, and libraries are there. If there's library, we always use it, but there are places where there's no libraries. And one other such example is SciPy coverage. For example, there is simply there's simply no libraries that covers all the SciPy service that we are encountering, like ND-image, stats, and so on. So for a lot of SciPy modules, we really have to write custom kernels in order to cover these functionalities and catch up with the upstream SciPy. So the conclusion here, to lead you to the next point I want to tell is that developers really need to be able to write code to target GPUs. We can have libraries as many as we can, but sometimes libraries are not there, and we need to be able to fill in the gaps, right? And before I move on to talk about how CuPy offers solutions to filling a gap, I do want to have two shout-outs. And the first shout-out is I want to thank the CZI fund provided by Trans-Zagbert initiative to cover the OSS development, and the CuPy was founded in EOSS 5 cycle, and so that we can use the fund to develop a lot of SciPy interpret module as well as a SciPy signal module. And in particular, we also want to thank the NVIDIA cuSignal team for kindly donated the entire cuSignal repo so that we can merge the whole cuSignal repo into CuPy, CuPyX.SciPy.signal, and that becomes the great coverage that we provide to cover SciPy signal APIs in collaboration with Preferred Networks and Quantsci Labs. And the second shout out I want to give is to Albert Steppe and Iron Zaid and several other SciPy maintainers to work on this new SciPy XSF repository, which is basically providing reusable code to cover special functions on both CPUs and GPUs. So using this code base, we are able to cover both SciPy.special modules, special module, as well as CuPyX.SciPy.special modules, so that both CPU and GPU code paths are covered by the same project, XSF. So I want to thank you for all the hard work you've made in the past 2 years. All right, so I mentioned that developers want to write code to target GPUs, and over the years, CuPy has been providing a wide variety of tools to help developers lower the entrance and write GPU code in Python. So the first thing I'm showing on the screen here is that there's a thing called element-wise kernel. You can construct element-wise kernel, and with the operation you want to apply in the kernel body, and then you compile this, you have this kernel automatically compile it for you and run element-wise in all the elements in your input array. For those who don't know what a kernel means, a kernel is just a function that you can run on GPU, but you have to invoke it from CPU. So you need to launch it on CPU, and then the work will be pushed to GPU and do the computation. And there's also reduction kernel. For example, there's an error2 norm example. You can compute a norm, square root of norm and return the array in the output. It works great, and under the hood, if possible, it's also accelerated by CuP, so you don't have to do anything if you just turn it on. And finally, there's also raw kernel. You can just, if you know how to write CUDA C++, then you can write your own CUDA C++ kernel and feed it in, wrap it into this with this raw kernel, so that this thing gets compiled automatically for you by CuPy, and then you can launch it with a specified degree and block size. So you have full control over the CUDA kernel that you write. So all these tools are great, but all these tools require you to more or less know a thing or two about C++ or CUDA C++. And so for a lot of Python native developers, this is still not ideal, right? They still have to learn a few things about CUDA C++. So can we do better is the next topic I will try to cover in my talk. So before I explain to you the solution provided by CuPy, I wanted to quickly give you a comparison, like what is CuPy doing in order to cover this case. So traditionally, you write the CUDA code in the .cu file, and then you send it to the NVIDIA compiler, NVCC, to generate either executable or a shared library. And NVCC internally will split up your code into two parts. One is the part that would be executed by CPU, and we send this host code to either GCC on Linux or MSVC on Windows and compile it into object files. And for the device kernels, then we send it to an internal compiler and generate architecture-specific binaries, and then we assemble them into a fate binary that's embedded in the executable. But for Python case, we really don't want to use NVCC for two reasons. Calling our executable using subprocess is just slow, right? So if it's in your hard loop, then your performance will not be good. And most importantly, it's really hard to redistribute GCC or MSVC. It's almost impossible. So it becomes a deployment challenge for Python users. They cannot just pip install them. Right, so we really want a solution that has a magic box under the hood, use either LLVM or MLIR or NVIDIA compiler libraries to do the job and generate kernels for you. So this is the kind of compilation I'm referring to. This is called just-in-time compilation or JIT compilation. And the gist is that it happens, all the compilation happens at runtime in process. Right, so there are two kinds of JIT happens in CuPy. There's a compiling CUDA kernels, C++ kernels to machine code, and compiling Python functions to CUDA C++ kernels. And you can see where I'm going. If I have a capability to compile Python function to C++ and then C++ to machine code, then I have a way to directly write Python code targeting GPUs. So why do we need a first JIT to begin with? Because to cover all the NumPy service, there is a combinatorial explosion in a number of kernels I have to compile and generate and ship in my binary. Taking this sum as an example, there are 14 built-in data types, 32 dimensions that following NumPy's footstep, and 14 output data types, and 15 GPU architectures we want to support times there are 2 CUDA versions, 4 Python versions, and 3 different platforms. So there's a lot of code you need to compile, and this is just one API. So it's virtually impossible if you want to do ahead of time compilation and generate a big binary and cover all the NumPy functionality. It's just too much, right? So the only feasible solution is that you compile it at runtime. So how do we do that? For JIT compilation, you can generate you can have a kernel string template that you assemble it at runtime, or you have user-provided kernels such as a CuPy raw kernel that we see earlier, or we have a JIT transpiler, which I will comment later. So in the case of a kernel string template, you can see that if I want to compute sign of a function, then basically I look at what's the input function data type, and NumPy promotion rule tell me what's the output data type I should have, and I can also look at what's the dimension of the input data type. Then I can generate all these snippets to feed into this template. Then I have a complete kernel body, then I can compile. So the idea is that I want to reuse these kind of templates over and over for different kind of scenarios so that I don't have to really write a bunch of kernels by hand. And the other thing is that I want to reduce the JIT compilation overhead. I want to amortize the cost. So the pipeline looks like this. You have kernel, you ask CuPy catch, assuming it is and it works, because it takes another talk to cover how catch works here, and it's quite sophisticated. Then you ask catch, is it a kernel cache or not? Oh, hey, if catch is cache on disk, we just load it from disk using driver API and then launch the kernel. Or it's already cached in memory, then it's even better, we just launch it without any loading. But if it's not cached, then we talk to NVRTC compiler library, we can programmatically compile the code and get the result back and catch it, then we follow this path. Right. Now, let me turn to a second JIT. So why is the second JIT needed, JITting the Python functions into CUDA C++ kernels? It's all because there is a function called NumPy.vectorize, where users write a Python function and then apply it elementwisely through this NumPy.vectorize API. But the same Python function just wouldn't run out of box on the GPUs, right? The instruction is different, everything is different. You really have to translate into the way that the GPU recognizes. So this prompts the need to actually compile this kernel into Python AST. And now, because I'm kind of running out of time, the same logic applies, except that now we have an AST to C++ transpiler that does the job for us. Basically, Python built-in library has this AST module, allows you to parse the source code of the Python function, and then from there you get the AST, which is abstract syntax tree, and you can visit all the nodes in the tree to kind of generate the C++ code. And in the end, we generate, for this particular user-defined function, we generate this code that we can embed in the LMOS kernel that I showed you earlier. But the brilliant observation here is that if we can compile this simple Python function, there's a ton of functions that we can actually compile using the same technology, right? So this is where the Numba-like compiler happens. You basically write the syntax very much close to the Numba compiler, but you can have grid and grid size to control the thread ID and the dimension of the thread block size and so on. And you can actually compile this code into a C++ kernel and then wrap it as a CuPy raw kernel. Then it gets compiled using the same trajectory that we already covered. So the compile code looks like this, and there are a lot of Python constructs and CUDA construct that we cover. And the best thing here is that you can inspect the outcome. So you can learn from it, you can debug from it, and if you you have a typo somewhere, the compiler will tell you that, hey, at which line you have a typo and why the compilation error happens and so on. So it helps you debug your kernel authoring. So back to this page, I want to say that we do now have a way to write Python kernels to target GPUs in CuPy. And this completes the last mile gap that we have before. So I won't have time to cover this. I want to give an outlook like there's a lot of work we want to do in the next few years, but for a small team like the one in Preferred Networks or NVIDIA or Quantside, it's a lot of work for a project growing to this great scope that we have. So it's not possible for any single team to carry out all these efforts. We really need your input to tell us which thing we should prioritize for, and we really need you to help us to evolve this project to the next stage. And I want to use this opportunity to congrats to CuPy for meeting the 10-year-old anniversary. And happy birthday, CuPy. And I also want to use this opportunity to acknowledge all the people that I've worked with on this CuPy project. I hope I don't miss anybody, but if I do, I apologize. And some of them has moved on from their previous affiliations, but most of them, and foremost, I want to thank the CuPy team and PFN because of their relentless effort. We now have a production-ready library to use for all things GPU. But also I want to thank all the CuPy contributors, users, and advocates. Thank you for your support. And this is all the NVIDIA sessions covering different aspects of GPU at SciPy. I'm here, but we will have more to come also in this forum. And with that, I want to thank you for your attention.
Thank you so much. So we probably have time for just a few questions, but that was an excellent talk. Okay, so we have a question from John. What's the relationship, if any, of this JIT approach and Numba CUDA? Are there fundamental reasons to have these different approaches? Right,
that's an excellent question. And so really the whole thing I was describing is a kind of a new attempt to see, because Numba CUDA started with Python bytecode instead of Python AST. So the original idea was that if we start with AST, and can we do something different? How hard is it to build a compiler from there? So I think this was the original intention, and also the original developer Imanish's intention. Right.
Okay, and then I'll use chair privilege to ask mine. So, yeah, so, wait, I see someone else typing, so maybe if you type fast. Okay, John just says thanks. All right, so I'll use my chair privilege. So you mentioned in your closing slide that you have ongoing work, or at least aspirational work, for CUDA wheels. So can you briefly talk a little bit about that? But I'll also just say thank you for having amazingly good CUDA support on Conda Forge. It's super nice.
Yeah, thank you. There's a lot of effort with the community and with multiple teams led by John Kirkham at NVIDIA. So the CUDA wheels is the story is like this. Currently, when you do pip install CuPy-CUDA 12x, it assumes that you have local CUDA toolkit installed. But we want to switch to use wheels that you can CUDA wheels that you can pip install. For example, cuPlus, cuSolver, cuFT, all these things can be pip installed as of today. So we want to move to use all these CUDA wheels instead of assuming that you have to install CUDA toolkit locally yourself.
Okay, great. So we're unfortunately out of time, but it looks like there's a few more people typing questions in there, so I think Leo can probably get in chat and answer those afterwards. But let's thank Leo once again for that excellent talk.
Thank you.